Okay, everybody, let's talk about homework 1.1. So this has been a while ago, but now that we're kind of at the end of the unit, it makes sense that all this stuff should be in review anyway. So let's just start with number one here. Use a diagram below to answer the following questions. Identify a set of constructors. In this case, we're talking about parallel constructors. So please recall that symbol means parallel. The geometric symbols typically will mimic the symbols you'd see or the structures you see in a diagram. So we have two lines that generally look parallel. So that's what you want to identify. Now, in the diagram itself, the parallelism is going to show up as these kind of chevrons or B marks. And so what we're really looking for is a set of constructors that are marked the same way. And so in this case, since they both have two V's, the fact that it's doubled up here doesn't really matter. They're in groups of two, and so they're in the same group as that one there. That's going to become our parallel constructors. And so our job now is just simply to name it. In terms of a name, how you want to put this together is really up to you, because even though they're both represented as lines, you can chop those lines up into something smaller like rays or segments, whatever have you, as long as you're using the letters as given. Just for the sake of argument, I'm going to stick to what's shown on the diagram, so I'm not going to try anything fancy like shortening rays to segments or whatever. I'm just going to go ahead and use what I have. So on the bottom one, we have CB. CB because those are going to be the two letters involved actually on that line. And then above it, I'll use the line indicator, so I have to make sure I put those two arrows there. I'll use a parallel symbol in between because that's proper notation. And now I have to name the top line. Now I do have a P, an A, and an L on that line, but I'm only required to use two of those letters to name it. And so I'll just pick two. It doesn't really matter which, as long as there's two on the line. So I'm just going to go PL, and again, represented as a line. And so this pattern is going to continue in, excuse me, in terms of analysis. First, we have to identify the symbol, which means in this case congruent, and then we have to find congruency symbols on the diagram itself. Now, congruency symbols are going to come in a couple different varieties. One, we're going to have those guys. Those tick marks indicate you have a linear constructor, a line segment in particular, that's going to be congruent. But we also have these guys, these angle symbols. And so recall, more than just segments can be congruent. In this case, we have angles as well. And so now we just have to name them. Again, the naming convention for linear constructors are 2 points. And so if I want to name like this line, this line segment, it'll be a C. Use a congruency symbol. And the matching tick marks, 2 marks to 2 marks, will be A, B. As far as the angles go, remember it's a where you start, where you go through, where you end kind of convention. And so for this upper angle, we have an angle that starts at P, runs through D, and ends up at A. And that's going to be congruent to an angle, in this case on the bottom. I'll just start at C. The only important letter here is the one in the middle. And so we have C to D to B. So C, D, and then over to B. Okay, so please don't get tricked into thinking the only things that can be congruent are line segments. Angles are in play as well. All right, next question. We're looking for this symbol now. That's perpendicular. And so what we're looking for on this diagram it would be a perpendicular symbol. You can't take this to necessarily be to scale, and so the symbols are really what's going to drive our work here. Unfortunately, if you look at this diagram, nothing is actually marked to be congruent. A perpendicular symbol would be like a right angle symbol, and so that's not where on the diagram we can't make the assumption that anything here is actually perpendicular, and therefore the correct answer here is none. There's nothing you can reliably say is perpendicular. As far as 2 rays and 2 segments, really the world's your oyster here as far as like what you want to name. Keep in mind when we're talking about a ray, we're talking about something that has a starting point and then continues in one direction. A segment has a starting and stopping point. But here's where your knowledge of geometric structure really comes into play. Now, there are certainly rays and there are certainly segments here, but there's too many really to give you a comprehensive list. The reason being is certainly you can see the ones that are pre-marked, but also consider in this upper line, PAL, you can say, well, here's a ray, AL. Or you can go the other way, here's a ray, AP. Even though it's part of a line, simply saying, well, I'm designating a starting point and going in one direction is enough to call it a ray. Same thing with a segment. Even though CB is a line, we can say, well, if we just consider this part of it, then we have a segment CB. And so I'm not going to list out all the possibilities here because it's simply too many. So just pick out some. The point of the question is to get you to realize or confirm that you realize that you can chop up the structures and kind of consider the pieces that you want. So let's move on to number 2. Construct a single diagram with the following directions. So our goal is to make one picture that has all this stuff in it. So let's start with the first thing, so sketch DC. So DC, D, and then C points. The structure itself is a line, and so let's mark it as a line. Pick a point A, then sketch AD, such that AD, in this case, is perpendicular to DC. So really that only means I can put it like above or below, otherwise it would not meet at a right angle. Just for the sake of this particular problem, I'm going to go ahead and pick it below. And so let's actually change colors here. So I'm going to pick a point A, then we'll sketch AD as a line, such as perpendicular. And the important part here is, since it is a hand sketch, I do have to show my intent, and my intent is a right angle, so I'd make that right angle sign. Next, pick a point B, then sketch AB, so you connect back to A, such that AB is parallel to my red line, my DC line, and is also perpendicular to my orange line. So that tells me like I can probably put it here. Okay, it doesn't really, this last one, AB is not the same length as DC, so I can't really put it there. Let me move it in a little bit. So it can't be the same length as the red line, but it has to be parallel to the red line, it has to be perpendicular to the orange line. And so AB as a segment has to be perpendicular, it has to be parallel to the top. Excuse me. And finally, sketch BC as a ray, such as BC is not parallel, so not parallel to AD. So AD is going to be this orange line, and so when I connect this with C, it cannot be parallel. Well, luckily I moved that in the previous step, and so it's not going to be parallel. Now we have to be really careful here. BC has to be a ray. Notice how it starts at C though. The symbolism here starts at C and goes through B. So I have to start at C. Ooh, that's terrible. C and take it through B. Okay. And so when you're doing this, like the thing you want to check for is 2 things. Number 1, are you using all the proper structures? So is DC a line? Is AD a line? Is AB a segment? And is BC a ray? That all matches. Second, you want to make sure all the relationship markers are shown well and also marked. Is a perpendicular shown? Yes, right there. Is a parallelism shown? Yep, I got my chevrons. I got another perpendicular here. There it is. And things that are not supposed to be equal don't look fairly equal. And so this diagram we can accept as being a pretty good representation of what we have for that problem. Okay, so number 3, explain the functional and technical difference between congruency and equivalency. Provide examples to help demonstrate your thinking. So this is something we've been talking about really since really early on in the course. Like there's always such thing as a functional and technical difference. And so when we talk about what that actually means, when you have a technical difference, you're talking about an exactness. There's an exact difference between things that we don't always every day observe. The reason we don't every day observe it is just because it's unnecessary to convey an idea. But that's what it. So if there's a technical difference, that's what that means. That also kind of hints at what a functional difference means. Like sometimes there is no functional difference between terms. If you kind of like if you think about like say a sport like basketball, if you call something a hoop or you call something a rim, that doesn't actually matter. Everyone knows what you're talking about, and even though it's actually called one of those things in like the rule book of the basketball of like NBA basketball, it doesn't actually matter which one you use. Another example I think I used in class was like a motor versus an engine. If you say, hey, look, my car's motor is not running well, or my car's engine is not running well, you're talking about the same thing, although there is a technical difference between a motor and an engine. And sometimes those things do not matter for the most part, unless you're trying to give like a technical description. So like in geometry, we have to go back and forth between those 2 ideas. In terms of geometry specifically, when we talk about congruency, we're always talking about structure. And we're talking about equivalency, we're always talking about values. And so in other words, like 2 chairs can be congruent, their measurements can be equivalent. And that's really the difference we're talking about when we're talking about congruency and equivalency, both on a technical and functional level. Like if I said, hey, I have these 2 line segments and they're equal to one another, that's technically wrong. Line segments can't be equal to one another, their measurements can be equal to one another. But functionally, I know what you're talking about, you know what you're talking about, everyone knows what you're talking about. And so that's something to keep in mind when you think about congruency versus equivalency. There's a functional and a technical difference there. All right, explain the difference between constructors and relationships in geometry. Provide a few examples of what you're thinking. So constructors are the things that form relationships. And so to use a non-math example, if you think about a relationship like marriage, marriage occurs between like two people, right? Or like a relationship occurs between a couple people. So the people would be like the constructors, the marriage would be the relationship. That's one of many examples, but like that's really what we're talking about when we're talking about the difference. And so when you think about the word constructors, we're thinking about like points, lines, planes, rays, angles, segments, and so on and so forth. When we're talking about relationships, we're talking about the things those things can be in. And so lines can be parallel, segments can be congruent, planes can be, perpendicular. Those things can be congruent. And again, there's more constructors in this list, there's more relationships in these lists, but the difference I don't want you to conflate here is that constructors are the things you need for relationships. In other words, like if there's a marriage, one can't exist unless there's at least two people involved. Like you can't marry yourself, for example. Like sure you can kind of do that, I guess, in your mind if you want to be super technical. But like as far as like a legal marriage or a legal kind of union, unless you have two people there, you simply can't accomplish that. And so if you just have a point by itself and you're saying, well, what's it congruent to or what's it equidistant to, you need a partner there to actually pair it with that. One segment cannot be congruent, two segments can be congruent. Okay? And so I'm going to stop here. This here part one. I will see you in part two of this video if you'd like to watch it. Thanks.